Okay, we're going to start chapter 11 now, which is a fairly long chapter, and it has to do with rational numbers. So today we're going to talk about rational numbers. We're then going to talk about square roots of variable expressions. We're going to talk about the Pythagorean theorem. We're going to multiply and divide and simplify radicals. We're going to add and subtract radicals. We're going to multiply binomials containing radicals, and we are going to solve simple radical equations. So there's quite a lot we're going to be doing in this chapter, so it's important that you keep up with the notes and the homework. Okay, so let's start with a basic definition. So a rational number is a real number that can be expressed as a quotient of two integers. So basically, I could say, well, is 3 a rational number? Well, I can write it as a quotient of two integers, which is basically just a fraction, okay, containing integers. So 3 is a rational number. If I have negative 1 4/5, I can write that as negative 9 over 5. These are both integers. It's a fraction containing integers. So I know that negative numbers can also be rational. If I have 48%, I can write 48% as 48 over 100. So that's rational. And if I have the decimal 0.6, I can write that as 6/10. So that is also rational. So rational numbers can be fractions, decimals, positives, negatives, percents. Okay, so most of the numbers that we're going to deal with are rational. Okay, let's look at inequalities, since we just did a chapter on inequalities. If I have these two numbers, so a, b, and c are positive integers, or a, b, and c can be any integer, and c and d are positive. So this is a rational number, and this is a rational number. And they're telling me that a over c is greater than b over d if and only if a times d is greater than b times c. So if you remember when we talked about cross products, we said we multiply our extremes, which are the a and a d, and we multiply our means, and we keep them in that order. If I do that, and my inequality doesn't change, then it tells me that this is true. So let's look at an example of that. So suppose I have 2/3, and I'm saying that that's greater than 1/2. And you say, well, I don't know if I agree with you, Mrs. Travis. So what we do is we can check it. We can say, well, 2 times 2 is 4, and 3 times 1 is 3, and 4 is greater than 3. So therefore, my fraction 2/3 must be greater than 1/2. Okay, so this is a good way to check if you have a bunch of fractions and you have to put them in the right order. You can determine whether they're less than or greater than. Here it's the same thing. A over c is less than b over d if and only if the product of the extremes is less than the product of the mean. So again, this is a great way of checking. If I have 2 over 7, and I say that that's less than 5 over 6, I can check it. That would be 12. That would be 35, and that is true. Okay, so that's just a good way of checking when you have fractions and you're comparing them to determine whether or not it's true. Okay, now we're going to look at the density property for rational numbers. And basically what this says is that if I have two rational numbers, it doesn't matter how close they are together, there is always another rational number in between them. And this goes on for infinity. There's an infinite number of rational numbers in between every single pair of rational numbers. So let's look at an example of how we would figure that out. So if I have 3/4 and 5/6, and I need to find a rational number that's in between these two. Okay, here's what I can do. First, I'm going to change them so that they have the same denominator. So my common denominator is going to be 24. So this is going to be 18 over 24. And this is going to be 20 over 24. And I say, well, the number in between 18 and 20 is 19. So 19 over 24 is a number in between those two. And it's actually halfway in between those two. If I have another number, suppose I have 2/4 and 3/4, and I want to find a number that's halfway in between. What I can do with that is, since there isn't an integer in between 2 and 3, I'm going to multiply both by 2. So this becomes 4 over 8. This becomes 6 over 8. And obviously in between those two is 5 over 8. So there's ways that you can find numbers that are halfway in between two others. And I could keep going. I could find a number in between these two, and then I could find a number in between those two, and I could just keep going forever and ever and ever. So if you ever get really bored, that's what you can do. Okay, so now we're down here. Any common fraction can be written as a decimal by dividing the numerator by the denominator. If the remainder is 0, the decimal is called a terminating, ending, or finite decimal. So you guys learned this back in 5th grade. When we have decimals, we can have one that ends. Okay, so like if I have 3/8 and I divide 3 by 8, I get 0.375 and it ends. Okay, so that's, we call that terminating. If I have, let's see, what's another example? If I have 4.3, no, that's already a decimal. If I have 4 and 1/4, I can write that as 4.25. Okay, again, so it ends. If I were dividing it, it wouldn't keep going. So those are terminating, ending, or finite. They all mean the same thing. Okay, then we have another type, which is decimal quotients that can be non-terminating, unending, or infinite. These are also called repeating or periodic because the same digit or block of digits repeats unendingly, and a bar is used to indicate the block of digits that repeats. So for example, if I have 2/3, which by the way is a rational number, and I divide it, it becomes 0.66666 forever and ever. And I would write that as 0.0 or 0.6 with just a bar over the 6, because 6 is what repeats. If I have, say I have 7/11, again, this is a rational number because I can write it as a fraction of two integers. If I were to divide that, I would get 0.636363 and so on forever. And so I could write that as 0.63 with a bar over both the 6 and the 3 because that is the block or the period that is repeating. Okay. So we have two types. We have terminating or ending, and then we have non-terminating or non-ending, which are repeating. Okay, these are all still rational numbers. So these are still rational, even though they repeat, because I can write them as a fraction of two integers. Okay, so for every integer n and every positive integer d, the decimal form of the rational number n over d either terminates or eventually repeats in a block of fewer than d digits. So basically what that says is if I have a rational number, I can write it as a decimal. It's either going to end or it's going to repeat, okay? And it will still be considered rational. Okay, the famous irrational number that you all know is pi. Pi is irrational because it cannot be written as a fraction and it doesn't repeat and it doesn't end. Okay, so that's a famous irrational number. Okay, but that's basically what this means. All right, so here we have a repeating decimal, and I need to write it as a fraction. So there's a fun and exciting way that you can take a repeating decimal and change it to a fraction of two integers. And so let me show you how it works. We use the letter n, just, I don't know, cause. And even though this is negative, I'm going to kind of ignore the negative. I know that when I'm finished, my fraction will be negative. So I'm just going to ignore the negative for now because it just kind of gets in the way. So I'm going to write this like that, except I need to actually write it the correct way. Like that. Okay, so this is what n is equal to. Then I'm going to look to see how many digits do I have repeating. I have 3 digits repeating. So I'm going to take this equation and I'm going to multiply it by 1,000. Okay, so everything in the equation gets multiplied by 1,000. Okay, normally if this wasn't repeating, it would get rid of the decimals. Okay, but watch what it does. This is going to move my decimal 1, 2, 3 spaces. So now I have 375, but it's still a repeating decimal. So it's still going to look like that. Okay. Now, what I do to one side, I can do to the other. So I have 1,000n is equal to 375 and 375 thousandths repeating. We know that this is equal. So I'm going to subtract the n on this side, and I'm going to subtract the 0.375 repeating on that side. 999n. When I do this, the repeating part disappears, cancels out. So I've gotten rid of the repeating part of the decimal. Now I just need to solve for n. And I'm going to divide both sides by 999 and see if I can simplify it. And in this case, I can simplify it to 125 over 333. Throw in my negative sign. And that is my fractional representation of that repeating decimal. Now here's something interesting that we can do. There are what we call true rational. So we're going to check to see if this is a true rational. And I've covered up my number. And I don't know if you're going to even be able to see this on the camera here. But if I take 125 and I divide it by 333, it does. It gives me that repeating decimal. So we say that this is a true rational. Okay, because if I take this fraction and I actually divide it, I do end up with this. Okay, so it's a true rational. All right, let's look at this next one. Here's another example. Suppose I have n is equal to 0.542, and this time only the 42 is repeating. So I'm going to multiply both sides by 100. And this is just 100n. And what this does is it's going to move my decimal 2 spaces. So this becomes 54, but this repeats, so it's going to go 242. I'm just going to write it like that. Okay. And then when I subtract, so this is where it's a little bit trickier. 99n. Notice that the 42 still cancels out. That was the whole idea of moving that. So if I subtract this, this is going to become 53.7. Okay. And so I'm going to have n is equal to 53.7 over 99. I can't have that decimal there, so I'm just going to multiply the top and the bottom by 10. I get 537 over 990, and that happens to simplify to 179 over 330. And if I were to divide this on my calculator, I do end up with this. So this is also a true rational. Okay. All right, so let's look at our proof now. We want to know which of these rational numbers is greater. Okay, so here's what we're going to do. We're going to multiply those, and we're going to multiply these, and it goes like this. So that tells me that negative 11/7 is less than negative 25/9. And actually, let's do this. I lied to you. Because it's negative, it's the other way around. All right. So yeah, you can't always ignore the negatives like I try to do. Negative 99 is greater than negative 175. Therefore, negative 11/7 is greater than negative 25/9. If they were positive, it would be the other way around. Okay. Here I have a repeating decimal, and I need to rewrite it as a fraction. Okay. Now I can ignore the negative until I'm finished. So I'm going to have n is equal to 0.415, and only the 5 is repeating. So I'm going to multiply both sides by 10. Multiplying by 10 is going to move this. So I have 4.155. Okay, I'm writing an extra 5 there so that I have this. When I subtract that, my repeating part will cancel out. So 9n is equal to 4. Actually, I've been lying to you a lot. 3.74. Okay, so n would then be 3.74 over 9. I have to multiply by 100 to get rid of the decimal. So I get 374 over 900, which is going to equal 187 over 450. And if I divide that, I get this, and it's negative. Okay, so that's what we have today so far for rational not numbers.